continuing with section 13.3, and we want to give some examples of arc-length parametrization. Example 4. Find an arc-length parametrization for the helix r of t equal to cosine of t, sine of t, and t. So what are the steps? First of all, find the arc-length function. So how do I find the arc-length function? Step 1, I have the parameterization, so take the derivative. And then find the magnitude of the parameter of the derivative. Square root of sine squared t plus cosine squared t and plus 1, and that is just square root of 2. Then the third is just take the antiderivative. Remember, when I'm writing s of t is integral, and let's say this starts from 0, and it's safe to assume that we start at the time 0 and then we end up at the time t. And this one has to be the variable that matches here, because it's we're finding the function. And then square root of 2, which is the magnitude of r prime of t, then d tau. And this is going to give me square root of 2 n equals 0 to t d tau, which is square root of 2 times t. Now, use this to find the parametrization. So now this is step 4. S of t is equal to square root of t. Now, what I'm doing here is that I found s as function of t, but if I want to change my parametrization over here, I have to be able to find t as a function of s. So how do I do that? I solve for t. That's how we find the inverse functions, right? So I solve for t. Solving for t here gives me t is equal to s divided by square root of 2. And then if I plug this back for t over here, and here, and here, then I get r as a function of, I get r of t of s. See, it's s of t, then it becomes t as a function of s is equal to cosine of t over square root, s over square root of 2 sine of s over square root of 2 and s over square root of 2. And you can call this q of s, or you can call it however function you want to name it. So we solved this problem, and it actually came out very nicely. I found q of s, and it was r of s over square root of 2, and it came out very nicely. But most times with the functions that are available to us, the parameterization is not going to end up so nicely. And so the next example will give you a glimpse of that there are only a few parameterizations that give you if you switch to arc-length parameterization, it would look nice. So arc-length parameterization example 5. This is section 13.3, and we're trying to find the arc-length parameterization for the curve r of t, t in the first component t, second t squared, the third t to the third. So as we go, first step of that is going to be taking the derivative, which is going to give me 1, 2t and 3t squared. Then you want to find the magnitude, and it's going to be square root of 1 plus 4t squared plus 9t to the 4th. And then you take the integral. Again, let's remember s of t is a function of t, so we start, let's say here is no starting from 0 also. Let's say start from 0. So the endpoints depends on where you want to start, and t, and then switch that integrand into for the dummy variable again, and d tau. Okay. And basically taking that integral, unless you're you hate yourself, is very difficult. And it's just very computational, and we don't really want to do this. And so what happens is that to be able to find the inverse function t of s and then plug it into here, I have to find that integral and then move on with it. But then for most of the Arclength parameterization that we have, the integrals are going to be very difficult to compute, or there will be only computed by numerical methods. And so what do we do? The beauty of this is that I know as t increases, the Arclength function is only increasing. And so for increasing functions, I know that the inverse always exists. So I know s of t is increasing, strictly increasing, and therefore I can find t of s exists, and that's how I know that there's a Arclength parametrization. So again, because s of t is increasing, s of t is going to be 1 to 1, therefore the inverse exists, and so the inverse is going to be t as a function of s. And so one other thing that is important is that s of t always exists. S of t, by fundamental theorem of calculus, always exists, and that's how we know there is an Arclength parametrization for every smooth curve. So again, any parameterization r of t of a smooth curve C can be used to find an Arclength parameterization of the curve, since s prime t is going to be magnitude of r prime t, is going to be bigger than 0, therefore s of t is increasing, therefore it has an inverse, and we think of t as a function of s, and we can express t as a function of s and replace it into the parameterization, and we get r of t of s, which is going to be the new parameterization q of s. Then the function q, the vector valued function q, has the same image as r, and parameterizes C as well. And then other qualities of Q is that if you're trying to find the magnitude of dq ds, if you want to find the magnitude of the derivative of the parameterization Q with respect to S, then by chain rule you will have this derivative is going to be dr dt times dt ds, And so when you take the magnitude of that, dt ds is going to be just a positive scalar come out, and then you have magnitude of dr dt. And so dr dt, which is r prime of t, and dt ds is the reciprocal of ds dt, which is again r prime of t, magnitude of r prime of t, and they simplify to 1. We discussed this before, but we just basically saying the speed of this parametrization is going to be 1. That also means that q prime of s is a unit tangent vector for all values s. Arclength question 13.3b. In a smooth curve, C is parameterized by a vector function r of t with the property that the magnitude of r prime of t is equal to 3 for all t. Which of the following is an Arclength parametrization of C? And so remember, you have to find the Arclength function, you have to inverse it, and then plug it back in and see what the answer is. So I suggest stopping it and stopping the video and coming back to it. So hopefully you stop the video, and so let's try to solve this question. And so the first step is done for me. First and second step is done for me. They already found the derivative of the parameterization and the magnitude of that. So all I need to do is s of t is equal to integral from 0 to t of 3 d tau, which is going to give me 3t, right? And so s is equal to 3t. If I solve for t, t is equal to s over 3. So the inverse function is s over 3, and that's what I'm supposed to plug into r of t. So I'm going to get r of s over 3, right? S is just a variable. Then I can just change the name of the variable. And let's go over here. Which one of these is matching that? And this would be the answer. Arclength question 13.3c. Which of the following is an Arclength parametrization of a circle of radius 4 centered at the origin? Remember, it says Arclength parametrization. It's just not any parametrization. So I suggest pausing the video and coming back to it. Let's solve this. So the first method that comes in mind is just take any parameterization, find the Arclength. So the circle of radius 4, r of t can be r of t can be 4 cosine t and 4 sine t, for example, or it can be or instead of that, I see a lot of them start with sine, so I'm going to get rid of that because that's not going to work very well in this case. So I go r of t equal to sine t and 4 sine t and 4 cosine t. And then I take the derivative of that. Again, this is going to give you a circle too. It's just that the points are going to follow differently this time. R prime of t is going to be 4 cosine t and negative 4 sine t. Then the magnitude is going to be 4. Then I take the integral 0 to t to find s of t of 4 d tau and d tau. And tau is like that little one line and then the circle on the bottom. And then this is going to be t 4t. So s is 4t. If I plug in t equal to s divided by 4, I should get the right number. And so s divided by 4, and which one do I have the answer? that is the answer. Is this the only way to find the answer? No, there is another way. What you can do is you can remember that if parametrization is Arclength parametrization, then the magnitude of r prime of t, or the speed, has to be 1. And so when I try to take the derivative of that one, I see the magnitude is going to be, for example, this one, the speed is going to be 4. This one, the speed is going to be 16. This one, the speed is going to be 4 again. With this one, the speed is going to be 1/4. That one is the correct answer. And so that's another way of finding out which one is the Arclength parameterization. So we're skipping a bunch of material in chapter 13 that are very, very interesting and important in physics. But the reason for it is, for how we discuss the motions in physics. The reason we're discussing it is so we can get to the theorems, the important theorems that are also important for physics and other area of science. And so what are we skipping? And so constructing a moving frame, which measures how the directions forward, inward, upward, and that sort of things along the curve, and then measure the curvature, how bendy the curve is, and how different it is from linearity, and measuring of the torsion, which is how the curve is deviating from lying on a plane, and also this is to my regret, we also basically skip the derivation of Kepler's law of planetary motion. There are a whole lot of nice videos online you can watch on how to drive that formula, and that was one of the first very accurate model for the astronomical universe, and it's worth watching that. After learning about this chapter, you can actually understand